Okay, guys. So I'm gonna make a little video about exam 4 review. So Alexis and I and Dr. Aguilar haven't been able to answer many questions this week. It's just a lot of family. So I'm gonna try to do this video really quickly. And if you have questions on any of the things that I've covered, or if I make a little mistake somewhere, let me know. Send me an email. And we won't be covering everything just because, again, I'm trying to do this like pretty fast. So nomenclature, all you. All right, but I can do degrees of unsaturation. Okay, it's whatever. So the first thing you do with degrees of unsaturation, you should have this formula memorized by now. I don't really do that whole like numerator over denominator thing just because I can't remember it, but I do carbons times 2. So we have a total of 10 carbons in this formula. Times 2 is equal to 20. And on the bottom, I'm writing the general formula. So then you do plus 2. That's what you do for every one of them. For our formula, I got 22. I don't know what you get whenever you input it into something else. And then you do minus the amount of hydrogens, which in this formula is 6. So I get 16. You get whatever you want here. And then you deal with your special atoms. So like if you have nitrogen, you add as many nitrogens as you have, or if you have halogens like how we have here, you subtract as many halogens as you have. So here we have 2 bromines, so I'll do minus 2. So minus X when you have halogens. X is the halogen. So I get 14 equals blank. And then you always at last divide by 2, and you should get 7. Again, doing this pretty fast, so let me know if I get that. All good. But this should be the general formula for all of them. And so I think the writing formula is just pretty hard. You'll have to go through a couple of structures, but I'm pretty sure that you get partial credit if you just fulfill the formula. Don't quote me, but pretty sure that's what happens. So let me try it. 1, 2, 3. So that's 10 carbons. And I have one pre-written. Whenever, like my strategy for this is whenever you really need to get rid of some degrees of unsaturation is adding like the triple bonds to the ends. So like if I did this right here, I already got rid of 4 degrees of unsaturation. And that is 1, 2, 3, 4. Let's see what else I did. And I just alternated with double bonds. I'm pretty sure that's good. Yeah, that should be 4. And then last thing I need to do is add my bromines. Add them anywhere. And then I'll count my hydrogens to make sure that I'm all good. So I'll circle it. 1, 2, 3, 4, 5, 6. There's something wrong. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, oh, I see what I did. I included an extra carbon. So there, if I add it down here, should be good. So let me try it again. One, 2, 3, 4, 5, 6. Okay, so that should fulfill the whole formula that we have up here. Okay. Next one, same process. So carbons, you multiply by 2. So I have 8 carbons in this one, times 2 is 16. Plus 2 always, something you always do, is 18. And then subtract the amount of hydrogens that you have. So I have 12 hydrogens, gives me 6. Do any special characters. So for nitrogens, again, you add as many nitrogens as you have. So plus 2 because I have 2 nitrogens. And I get this. That's good. I get 8, and then last step always is to divide by 2, so I get 4 degrees of unsaturation. And so I have one pre-written out for myself as well, because again, these structures take pretty long, so just experiment with them. 1, 2, 3, 4, 5, 6, 7, 8. All right, cool. So this one's what I have written out. I like to write the hydrogen on that one just because, I don't know, sometimes I forget. All right, that's the one that I had written out. I played with it like about 3 times to get this. So again, just as long as you get your formula right and then start playing with the degrees of unsaturation, you should be good. So let me count really quick. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens, 8 carbons, 2 nitrogens, 1 oxygen. Okay, cool. And again, you can do any functional group. The degrees of unsaturation that I did here were these 2, this one right here, and this one right here. So 4 in total. Cool. The next one, so I'm gonna write out the products for them, and then I'll just discuss it with you, and I won't write anything down for, like, you can create your own explanations for it. You have them in your notes. I'll do a little like quick review. For the hydroboration oxidation reaction, we know that it's regioselective for the most steric, the least steric behavior. There you go. So I won't draw out the whole mechanism, but the BH3, which I believe is just BH2. I have the mechanisms with me in case I had to refer back to them. And I'll send you guys my notes that I'm looking at right now. Yeah, it adds on as BH2. And it goes to the least substituted or around the least sterics. And so I added it to the primary position right here, instead of the secondary position. You're always adding it between the 2 double bonds though, which is why I only circled these 2. Okay, so I added it, least steric. Okay, cool. So that was the first thing. And so the reason that it adds there's like 2 explanations for it. I'm pretty sure we didn't get into the electro whatever part, but we did do sterics. And so the sterics part of it is when you start adding that BH3 to it, you don't want to sterics argument. I don't know. This is the whole thing about it. And you can find it in your book, you can find it in your notes, more especially. Yeah, and then the second part is just the replacement. They don't show it to you in the book or in class. You can find it online if you want to see it. Yeah, but for this one, sterics argument, and you can come up with the whole sentence that you want to put, but we're probably gonna look at something else like this in the test, so it's good to get down your explanation now. Another way that you can see this is just BH3 or BH3 with THF or 9BBN. So if you see that on your test, don't get confused. It'll be the same. For the next one, I believe it's the hydration reaction. Yeah, hydration reaction. And so the first step in the mechanism for this one, if you have an acid and you have a base, which in this case it's your alkene, acid-base reaction first. And so when you do that acid-base reaction first, you want to put the hydrogen in the place where it can make a stable carbocation. So if I put the hydrogen in the least substituted position, I make a secondary carbocation instead of the other way where I would make a primary carbocation, which absolutely not. And so the next step is nucleophile attack. So in this case, this is our nucleophile. It attacks, and then at the end of the mechanism, H2SO4's conjugate base has to come back and deprotonate. And so what you should get is this. And so the thing that they were looking for, or the regioselectivity that they were talking about, is notice how on the left reaction we have a primary alcohol, whereas on the right reaction we have the secondary alcohol. And they're just asking you for the explanations, and the explanations are usually just found in the mechanisms. Cool. This one was cool. I stared at it for like long. Okay. Let's do it for the first one. And I'll try to breeze through this. The reason I'm writing it like this is because you want to show connectivity. We take off points for connectivity. So make sure you write it like that. Let's see. This next part where you have to decide where the hydrogen goes for that first step that I just did, it's usually based on the product that we're talking about. So this first one's asking for the formation of A. And wherever you put your carbocation is wherever your nucleophile H2O is going to attack. So basically, wherever you put your carbocation is where this OH should be. So then that's why I'm going to put my hydrogen right here so that my carbocation forms right here. H2O can attack with its lone pairs. But it has a positive charge right now. So you can get rid of that positive charge, make it a neutral compound, and come up with compound A. This compound A, yes. Yeah, so a thing that I always saw is forgetting the deprotonation step. Don't forget this step. Our acid is our catalyst. So catalysts always reform at the end. And so that's why in the end it was this plus the catalyst reformation. But I don't believe you have to form or put the catalyst in the last step. If you put it, it's totally fine. Curved arrows for B. Okay. Okay. So always, first step, go strong acid, protonate. We just need to know where to protonate. And so when I'm looking at compound B, I notice how initially I had my two methyl groups on the top, and now one of them moved. So I'm thinking methyl shift. And so I want to put my carbocation closer to those two methyl groups just because we're gonna have to do a methyl shift. So I need those methyl groups close. I'm gonna put my carbocation up here, my hydrogen down here. Let me zoom in because we have to do that. This whole methyl group, and I go from the bond because those are where my electrons are. And so that whole methyl group is going to go ahead and attack or act as a nucleophile to that electrophile, the carbocation. So it just moves. Oh, I didn't write the rest of the. Yeah, just remind me to write the rest of the reaction. It looks so bad. Okay. Whatever. It's fine. So boom, I moved it here. And now I have a carbocation right here. Because I used to have 4 bonds there, and now I have 3. I'll leave that other hydrogen alone. And so I'm going to look back at B, and it looks like, again, wherever you have your carbocation is where you put your OH group. And so it looks like this is where my carbocation should be. And so again, H2O is your nucleophile. It's electrons. I usually like to draw my electrons. Attack. And then you need another deprotonation step because you're going to have a positive little charge on here. So again, as always, this acid is your catalyst, so it should be regenerated. Does it look the same? Yeah, it does. This one is harder. Okay, let's start with our initial thing. Okay. Each step is a couple of points. The first step, every time you see an acid, is protonate. If you can't get all of this mechanism, get one part of it, and you get points. So this is already like, I believe this is 2 points, because I believe we do points for every arrow. So now I have to determine where my carbocation should be. Honestly, like, you can try this out. So I tried it out to where I put my carbocation right here, or I put my carbocation right here. It was like really trial and error for me. Maybe you have little tricks to do it, so let me know so I can tell everyone else about it. This is what I ended up finding out. All right, I protonated. So now I need to, it's obviously going to be a methyl shift because we're rearranging carbons. Like this does not look like this. So there's going to be some type of methyl shift. And if you remember from the lectures, you can do methyl shifts and completely rearrange the whole compound. So like can be a 6-membered ring here, but it can go to a 5-membered ring. So that's when you really start thinking, am I doing a hydride shift, which is no, or am I doing a methyl shift where I can probably shift the whole compound around? So I'm doing a methyl shift here. I just need to figure out what methyl. By the looks of it, I have 2 methyl groups that are the same. So like on the NMR, you would get like 6 hydrogen integration. And so it sounds like these I don't even mess with. So I'm not gonna do any hydrogen shifts with that. What I wanted to do, because I feel like that kind of narrowed it down a little bit more. I wanted to use this bond. So from the bond, and I wanted to attack this. And I'll see where that takes me. And so I'm going to number pretty much like the nucleophile all the way to the electrophile. This is interesting. Did I do something? Oh. Okay, so again, trial and error. I believe carbocation goes right here. And the reason I knew that is because when I was numbering, I was like, wait, this would make a 4-membered ring. And so that's pretty much what told me. I move this right here. Keep my structure of the left compound. But now I have a 5-membered ring. So the part that's fused to that cyclohexane is going to remain as 1 and 2. And then you can start numbering the rest from there. 4, 5. Don't forget, I feel like counting your carbons is a big thing here. So I have a total of 3 carbons right here. And these 3 carbons are going to be coming off of my carbon number 5 that I just numbered. It looks a little like that. And so since I broke this bond right here to a carbon that has 4 bonds right now, this right here has my carbocation. And again, wherever your carbocation is, your OH will be in this reaction. And so you can do that whole thing again, where H2O is your nucleophile. You do a whole deprotonation step. Don't forget your charges. We also take points off for that. And let's see if it looks like compound C. Yeah, compound C. Okay, cool. I pretty much rushed through that too, so let me know if I did anything wrong or if you have any questions. Someone was on the quiz and I just wanted to go over it with you guys really quick. Pretty sure I gave some of you some points. And this is what the points that might not have been like, I'll show you. So if this looks similar to you, you should have been like, oh, oops. Okay. Whenever you have an acid, it pronates. And so find your base, which is usually an electronegative atom, and protonate. This is already 2 points right there. Don't forget any carbons, because if you forget your carbons, the whole compound is wrong. The whole rest of your mechanism will be wrong. So you protonated it, and you have protonated ether. Okay, I'm gonna change my colors. I don't know if you remember in class, but whenever you protonated ethers, that's when they were like SN1-like. And so when they're SN1-like, we remember that we only like attacking the most sterically hindered positions. So then we start comparing the two electrophilic positions right here. And we're like, okay, so this is SN1-like, I should be attacking the most sterically hindered. And so my iodine from back here is gonna come back, but attack the most sterically hindered position. And you break the bond right there. Again, I suggest numbering your carbons or atoms, however you would like. Just that 1, 2, 3, 4. 1, 2, 3, 4, 5. Just so that you don't drop anything. 5, 4, 3, 2, 1. Okay, so on carbon number 1, I had 2 methyl groups. And now an iodine because I attacked. And on carbon number 4, I had an OH group. And the oxygen is number 5. Yeah, it looks like I have that so far. Next thing, you put 2 equivalents for a reason. So you're going to be using those 2 equivalents. You have an acid, you have a base. Boom, make a good leaving, make a good leaving group. You have to put that arrow. All right, perfect. Okay, so then have a good leaving group. You still have that iodine that left. It's going to come back. And can't do an E1 reaction the SN1 reaction. And I saw a lot of you kind of put carbocations in the primary position. Remember, carbocations in the primary position don't exist. Very, very unstable. So then we have to do an SN2 reaction right here, because it's not possible to do that carbocation. One, two, three. Yeah, mine looks a little different from there because I didn't structure it the same, but this is the same compound. Just flip it around. Let me know if I dropped any carbons, but I counted. I'm pretty sure this is good. Some of you guys, what I saw was that you did it the other way around, where you did the SN2 reaction first, and then not the SN2 reaction, where you attacked this one first. Just remember, whenever you protonate the ether, whenever you have acid with an ether, that's when you're doing the SN1-like reaction. So you're going to want to attack the most sterically hindered position, which would not have been this one right here. Synthesis, I'll let you guys try that. I'm pretty sure Dr. Aguilar wants the critical thinking to you guys. So synthesis and NMR I won't do today. You can always ask during office hours because we'll be having office hours tomorrow. Mechanisms and everything. I won't do the mechanisms for all of them because you can find them in the book, but I will show you the products for them. It says major products. So this is the hydration reaction. So where you're actually adding the H2O. So first step, I'll talk you through it. So first step, you make the carbocation after protonating the alkene. And so we make the carbocation in the most stable position, which would be the tertiary position. And then the nucleophile, which is H2O, can attack. And you know, wherever the carbocation is in the hydration reaction, that's where the OH group is. Yeah, so that should be good. This next one, let me just write out the base structure. This is where you do the halogen bridge and everything. So those arrows that are concerted to a bromine while one of them leaves. You're doing that whole halogen bridge, and the bromine that left initially is coming back to attack probably the least directly hindered one. But what you get with this is, let me see if it's on the same side. I'm pretty sure it's on the, I'll just do it like that. Yeah, cool. Now, I feel like a lot of the times we would get confused with like if it was bromine and H2O. If it's bromine and H2O, you have a different nucleophile this time, and it'll be the water as a nucleophile whenever you make that halogen bridge. And the reason being is because we're using H2O as our solvent, and so there's so much water in the solution, so it can act as our nucleophile immediately. And so instead of having a reaction with just or a product with just the two bromines on it, when you have that bromine H2O reaction, you're going to have an OH group and a bromine. So it's the little things like that, which I mean, when you do the mechanisms, they make sense. But I don't know where I was going with that. So let's go. HCl2 is a forced E2 reaction. This one is I would say a pretty big mechanism, but it's an E2 reaction, forced E2. So then they have to be antiperiplanar, the leaving group, which will be my OH group along with the process, and the beta hydrogens. So my two beta hydrogens are this one right here, and then I have two on this side. Okay, yeah. I'm pretty sure when you start making that that good leaving group with the pockle, it doesn't change any stereochemistry. So then you're looking for, you have the good leaving group on a wedge. So you're looking for a beta hydrogen on the dash. So then what's probably going to happen is I'm going to eliminate on this side. So I eliminate on that side. And then don't forget to retain the stereochemistry on this side, or on the left side, because you didn't mess with that at all. And that should be good. Again, go through the mechanisms for those. This one, I kind of looked at it. This is a hard NMR because it's symmetrical, but you can reason through it just by doing the mechanism. And so mechanism, I'll go through it pretty fast. Remember, you have an acid, look for your base, and protonate. Really cool. And so I kind of got confused really quick, but I had explained before that whenever we kind of get confused, or personally, I got confused whenever I saw H2SO4 and I'd be like, okay, is this an elimination or an addition reaction? Usually when you see an alkene and H2SO4 along with something else, it's going to be an addition reaction. Whenever you don't see an alkene in your reagents and your starting materials, and you see an OH group, it's probably going to be, you're going from that OH group to an elimination. So that's exactly what I'll do here. It's a secondary, the leaving group is in the secondary carbon. So I'm going to go ahead and say that that leaving group leaves, and I have a carbocation. For this carbocation, I'm thinking, okay, can I do a hydride shift? I can, but it won't put it in a stable position. Can I do a methyl shift? Yes, and it will put it in a stable position. And so saying stable position because watch what happens when I mess with this. So I move that methyl group over there. This no longer has its 4 bonds, so this one has a carbocation. And so now my carbocation is in the tertiary position, whereas before it had been in the secondary position. So you can only do methyl shifts when you actually make a change to it. So if I went from secondary to secondary, no use. If I went from tertiary to tertiary, no use in doing a methyl shift. Here there was a use though, so this was good. And so the last step is just deprotonating the I guess it's beta hydrogen, I think is this term. And so OSO3H minus, because this is a catalyst, it has to be regenerated. So I'll put this down and I'll put this down. So my goal for this one was trying to make the more stable stable carbocations, more stable product, because this is a tetra substituted. And I pretty much just checked myself with the NMR. And so we can just check it really quick, because the NMR here is confusing. If the NMR doesn't help you, then don't pay attention to it. You can just confirm. And then if it's no confirmation, then you can try the mechanism again. Like you want those points, so then just try to go through it fast. When confirm, so I'm going to confirm this one first. 6 hydrogens, and that's because they're in identical chemical environments. So there is no hydrogen neighbors right here, which explains why this one is a singlet. 6 hydrogens, I mean, I've said this before, anything with the empirical formula of 3, or you can multiply by, empirical formula of 3. So 3, 6, 9, 12, all of those are usually terminal carbons, and that's because terminal carbons usually have 3 hydrogens at the end. And so this last one, where we had an integration of 6, it's probably these terminal carbons. They're in similar chemical environments, and they're what's it called? Sextet, triplet. I don't know why I blanked out. So they're triplets. And so that means that they have 2 hydrogen neighbors, and that's totally explained by these 2 hydrogen neighbors right here. So let me really quickly, because I know you guys like the highlighting stuff, so let me try to highlight it. And then these last two hydrogens that we were talking about, again, they are symmetrical. This is a symmetrical molecule if you cut it in half. Symmetrical. And so with symmetrical molecules, you have similar chemical environments and the similar positions. And so you add up the integration. So instead of just having those 2 hydrogen integration, it's a total of 4, because again, they're identical chemical environments. So then these 4 hydrogens that I just kind of wrote out, is this right here. And of course, you can explain it because this is a quartet and you only have 3 hydrogen neighbors. Let's go to our reactions page. Again, I won't go through the roadmap either. Okay, reactions page. I would say a lot of the times in Ochem 1, I would do the mechanism just because it would help me. But I'll just kind of go like through the outlines for each reaction. So for the first step in A, the TSCl pyridine, all this is doing is making a good leaving group. So I'll show you the intermediates, but make sure to read the problem and ask if it asks for intermediates. But for this first part, just making a good leaving group, and it retains stereochemistry. OTS, great leaving group. Reaction 2. So big bulky base, and whenever you see potassium terbutoxide, it's usually going to be an elimination reaction. And so let's see what we'll do here. It's a strong nucleophile, so it's probably going to be E2. E2 reaction. E2 needs antiperiplanar, so that means that your leaving group and your beta hydrogen have to be in different spatial orientations. There you go. And so this hydrogen right here, same spatial orientation, but these hydrogen right here, different spatial orientations. So these two are antiperiplanar to each other, so I can do my elimination reaction on that side. Talking really fast. Let me see. All good. This next one. So previously we were talking about if you have an ether and you have something to protonate it with, that's when you do the SN1 like reaction where you attack the more sterically hindered position. In this position, we have an ether, but we don't have an acid. So then we're probably going to be attacking the least sterically hindered position. And so between their two electrophiles, these two right here, our least sterically hindered position is this one right there. So then I'll draw the base structure. Cross out this. This is a strong nucleophile. So this is going to attack my electrophile, and you break this bond over there. So if this methyl group was on the wedge, then this OH group has to be on the dash. And we output stereochemistry again, since usually in ethers, both of those two lines that you see connecting to that oxygen are going to be on the same side. Either they're both a wedge or both a dash. In this case, this methyl group tells us that the bonds for the ether are on dashes because you can't have two things in the wedges, right? So this has to be on a dash. That means this other one has to be on a dash. So a whole lot of things. Okay. So it attacks, and it has to be a backside attack. So then that's why I changed the configuration on that bottom one. That's CH2CH3. Cool. So that'll be your nucleophile. It looks a little bit weird, but just remember when you see a metal, cross it out and then see what your nucleophile is. Usually our nucleophile is right next to the metal. So my sulfur was the metal and it attacked my electrophile. So it should be directly connected to that carbon. So don't rearrange it because again, we take off points for connectivity. And then the last part, which is the H2O, which all it does is protonate, and we're protonating the oxyanion that we just made. Okay, here we go. Next one, again, to be honest, the whole reactions page, I feel like what we mess up on the most is the stereochemistry. So again, I'll send you my notes for my stereochemistry, but just remember, whenever you add to the alkene with like the halogen bridges stuff, so whenever you have a halogen, it makes a halogen bridge, they have to be on the same like either both on the wedge or both on the dash. So kind of showing a little bit of the mechanism, not really. I'm not showing you the arrows, but the first step is making this intermediate. And so the bromine that comes from the mechanism comes and attacks, and it has to be from the back. And so that's why in my product, what I'm going to write is one BR on the wedge, the other BR on the dash. And I'm also going to do the enantiomer. They might be the same. Might be the same. I'm pretty sure they are the same, but again, it doesn't hurt to write it out. We don't take off points for you writing it extra. So I could have attacked from the front or the back or whatever. Cool. Next one, PBr3 is a inversion of stereochemistry and adds a bromine instead of the OH group. Again, I'm not going to the mechanism, but I can kind of tell you a little bit about the notes for it or how to go about it fast. Again, it's inversion of stereochemistry of the OH group, and you're just adding the bromine. Let me just check myself real quick. It's actually good. Yeah, cool. Next one, NBS. NBS is a source for bromine. I would suggest that you know the structure of NBS. This is the structure for NBS, and it could probably be asked in the nomenclature part, but all you should think about when you see NBS is the bromine. So it's N-bromosuccinimide, so that B right there means bromine. So whenever you see bromine and an alkene together, you're probably going to make that halogen bridge. So I won't show you the arrows for the mechanism, but pretty much goes with the same way you make that halogen bridge. So you have that halogen bridge after step 1. I'll call this the intermediate for step 1. And so step 2, which is DMSO and H2O, is going to be like an SN2 reaction. You have your nucleophile, which is H2O, and so it attacks, I believe it will attack this position. We should definitely ask on this one. We'll ask on this one because I don't remember any like required stereochem or configurations for this one. But as long as you get like some details out of this, MBS provides you bromine, so you'll get this down, and you'll probably get this as well. I'm gonna go ahead and guess you can add it to either side. And we can look this up. So it can also be we'll look this up. But they are anti-addition. So there's so they'll be on opposite sides. The bromine and the OH group will be on opposite sides. And that again is because the halogen bridge, both of them should either be both on the dash or both on the wedge, and something attacks from the back. So then they'll go off to different ones. One on the wedge, one on the dash. So yeah, ask about this one for sure. This next one, this is it's a base. So very strong base. Cross out this, put the negative charge. I'm gonna go ahead and take this proton away. So this is a hydride. That's why it's negatively charged. And so I'm not messing with any of these bonds right here. So retain stereochem for that. So then the first intermediate for this one is just gonna be your anion. And then the second step, this right here looks like this, which we know alkyl halides are pretty good, or are electrophiles. So I'll move this up. Nucleophile attacks electrophile, leaving group leaves. Again, not messing with any of the other bonds. So you're fine. Let me change my color. You're fine to leave all the stereochemistry as is, but you are creating an ether. Don't drop any carbons. So I put a total of 2 carbons because that is what I'm adding on right there. And don't mess with anything else. The HBr one, go through the whole mechanism. This is what I got. Please let me know if you got the same things. Oh, this is bad. Sure. Pretty much cut this off. Put an OH group on both sides. Next one, the hydroboration oxidation. So again, the first step is to put the borohydride, sorry, I'm thinking about another reaction, huh? Put the BH3 on the less substituted position again because of sterics. You don't want to put it near something big and bulky. So right here. And so the next reaction they don't really talk about, but you know, it's just you switch them out. So instead of BH2, it'll be OH. I didn't mess with the methyl group, so I don't do anything to it. And then we can check their stereochemistry here, but this is for sure the structure. And I'm not really too sure about any stereochemistry for this one, so we can ask about stereochemistry for this one as well whenever we have office hours tomorrow. So I'll go through NMR. You can try it on your own, and then we'll check it in office hours. Let me just insert this right here. Again, the mechanisms you can go through in your book. Synthesis, I won't go through that. Again, we can check it for you. Right. Yeah, then this will conclude our practice exam. Maybe I'll be able to do an office hours before Aguilar's office hours begins for those of you that can't make it at the time. But I don't know, because tomorrow I have a pretty busy schedule. So we'll see. I'll send this out right now and then let me know if you guys have any questions.